Okay, this lecture is about bandwidth limitation with phantom zeros. There can be situations in which we design the controller of a negative feedback amplifier and we end up with too much bandwidth, with more bandwidth than we need, let's put it that way. A reason can be, for example, that we need a lot of stages in order to get the current or voltage drive capability. Or we need a lot of stages in order to have the distortion as low as required. This often is the case in audio power amplifiers, if they're not Class D amplifiers. In audio power amplifiers, where we need a lot of power gain because we have a very low impedance load and a high impedance signal source, and we need a lot of voltage gain usually. And so we need many stages, and all these stages contribute poles, contribute to the loop gain pulse product, enlarge the bandwidth, and we need them just because of distortion and not because of that bandwidth. In such situations, you would like to limit the bandwidth, and we have already seen last time that we can just in a brute force way place capacitors in parallel with the signal path or inductors in series with the signal path to limit the bandwidth. But there's also a smarter way, and that is what I would like to talk about in this lecture. So first, let's go back to the phantom zero compensation, because that is the basics from which we are departing in this lecture. So here I made an example of a trans impedance amplifier with a capacitive current source, resistive feedback, and no load, because the controller is modeled as an ideal voltage controlled voltage source. So it's no use of putting any load there. It wouldn't affect anything. And the controller has been given a pole in the origin and optionally a second pole that we can play with later on. So we start with having no feedback capacitance. Its feedback capacitance is intended for phantom zero compensation, and also this second pole in the controller, we put it to infinity. We take some gain in the controller of 10 meg, and we have some values for RF and CS for the feedback resistance and the source capacitance. The loop gain reference for evaluating the loop gain is the voltage controlled voltage source. And my first question to you is, how many poles does the loop gain have in this situation? Well, obviously, if I look at the result, many of you are looking to the circuit and see just one capacitor because CF equals 0, and therefore say there is only one pole. That is my assumption. But don't forget, there's also a pole in the origin in the transfer of the voltage controlled voltage source, because it states A over S there, and S is still a plus variable. So this system has two poles. Be aware, this kind of questions can be exam questions. So really look carefully at the circuit and try to don't try to skip anything. So my next question requires you to have a calculator or to estimate very well by just, from hand calculations. How many dominant poles does the circuit have? This is also a question you should be able to answer after the bachelor course already, because there's nothing new here on transistor level. Now, there was a procedure for finding the number of dominant poles. You could say rank the poles in the order of magnitude, and then check the first order, the second order, the third order, bandwidth, etc., and take the smallest one. Or if a next pole is larger than the bandwidth you calculated with the previous one, it is not dominant. So let's see. The first pole is in the origin, is at 0 hertz. But that doesn't mean that any other pole will be dominant, of course. The product of contribution to loop gain and pole of this first pole is A. So if there would only be this dominant pole, the product of the loop gain and the dominant pole would be A, and A is 10 megahertz then. So the bandwidth would be 10 megahertz if there is only one dominant pole. If there were a second dominant pole, then the second pole is formed by R2 and CS. Then the time constant of R2 and CS should correspond with a frequency smaller than 10 megahertz. Well, that is 10 kilo ohm and 300 picofarad, which is 3000 pico uh, nanoseconds, which is definitely dominant. So we have two dominant poles. And if you calculate it properly, we have a pole in the origin and a second pole uh, at 53 kilohertz. And the product of the loop gains and the poles, you can find the bandwidth from that. And that is what I was doing here, was 410 kilohertz, which means both poles are within this bandwidth. There is no third pole, so they are both dominant poles. This can also be a question for the exam. So if you don't know this procedure, go back to the feedback model and the controller properties from the bachelor course. So next question is, can we compensate such a system to a maximally flat magnitude characteristic with the aid of a phantom zero? Phantom zero compensation is possible if the minus the sum of the poles is smaller than the square root of 2 times the achievable bandwidth. The achievable bandwidth here is 410 kilohertz, and the square root of 2 times the achievable bandwidth is about 600 kilohertz, and the sum of the poles minus the sum of the poles must be smaller than 600 kilohertz to have compensation possible with a phantom zero. So that is definitely the case. It's a factor 10 smaller, more than a factor 10. So we can compensate it, and you can use the expression that is derived in the book. And it's from this you can find the compensation capacitance that we need for that, and you will find 50 picofarad. But I'm still not finished with the questions because the next question is, does this implementation of the phantom zero affect the bandwidth? How can you estimate it in a quick way? Well, you see in the expression for the second pole that there is both CS and CF. So if there is no CF, we have a capacitance there of 300 PF. And if we add 50 PF to CF, then we have 350 PF. So the product of the poles changes with 300 divided by 350. And that is the product of the pole, and the bandwidth is just the square root of the product of the poles, proportional with the square root of the product of the poles. So if you do 300 divided by 350, and you take the square root of that, then you find that the bandwidth will be approximately 8% smaller than after compensation. So that is why yes, but less than 20% is the correct answer.